Hello again. We're now on chapter 2 of Landau Lifshitz. So we're doing a chapter 2, problem 1 in the mechanics textbook. And this one is a little bit more interesting than what we were doing before. So now we have a particle, the specific mass, that's moving from one region in which the potential energy is a known value to another region in which the potential energy is a different value. And the boundary between those two regions is a full plane in 3D space. So that makes each of the two regions a half space, i.e., it takes up half of all space. And our goal is to determine how the motion of this particle changes as it crosses that boundary. We know that within any region of constant potential, the velocity will be constant, that the velocity will change as it crosses the boundary. So I'll start by drawing the situation. We've got the dotted line representing the boundary, and the particle moving with a certain initial velocity, v1. And that v1 has an angle from the horizontal of theta1. Sometime later, the particle will be on the other side of the boundary with a different velocity at a different angle. So we have v2 and we have theta2. The principle that we're going to be using to solve this problem is conservation. And in particular, due to vertical translational symmetry, we know that the vertical momentum will be conserved. Additionally, we know that the energy will be conserved. These two conservations will allow us to solve this problem. So we have that the vertical component of the momentum will be the same on the left and the right. And here I've excluded the mass because the mass of the particle does not change. And we can use this expression along with the expression for energy of conservation to solve for a relation between theta1 and theta2. So now that we have the conservation of energy equation, we can use it to eliminate V2. And we do this by plugging in an expression for V2 that we got from our momentum conservation expression. And to finish it up, we can isolate sine of theta 1 divided by sine of theta 2 to have a more direct relationship between theta 1 and theta 2. And with that, we're done with question 1 from chapter 2. And I'll see you all next time.